In this video, I will show you how to solve problems involving proportionality and differential equations. Problem 1. If dy dx equals 2y and y equals 1 when x equals 0, what is the value of x when y equals 3? This is a separable differential equation, so we want to get all of the y values on the left and all of the x values on the right. To begin, let's multiply both sides of the equation by dx. That'll get the dx over here on the right. So we will have dy is equal to 2y dx. Now we want to get this 2y over here on the left. So let's divide both sides by 2y. Then we will have 1 over 2y dy is equal to dx. Now that we have all of the y's on the left and the x's on the right, we can integrate both sides of the equation. I'm going to bring this 2 in the denominator out in the front before I integrate, so that's going to be a 1/2 times the integral of 1 over y dy is equal to the integral of dx. Maybe I'll just put a 1 in here to make it more obvious what's going on. On the left, we have a memorized rule. The integral of 1 over y dy is the natural log of the absolute value of y plus c. I'll save the plus c for the right-hand side. The antiderivative of 1 is x, so x plus c. Let's use this initial condition to find the value of c. Substituting 1 for y and 0 for x, we have this. We know that the natural log of 1 is 0, so on the left-hand side we just have 0. And on the right-hand side we just have c. So c is 0, we can substitute this in, but that means it's gone. This is the solution to the differential equation. Let's use it to find the value of x when y is 3. So substituting 3 for y, we have 1/2 natural log of 3, and that equals x. So this is the answer. Using properties of logarithms, we can take this coefficient of 1/2 and put it as the exponent. So you might see the answer also written as x equals natural log of 3 to the 1/2 power, but this really is the square root of 3, so you would more likely see it written this way. And this is how the answer would most likely appear on a multiple choice question. There is another way of solving problem number 1 that I want to show you. It involves a shortcut that I would like you to memorize. Anytime you have a differential equation in the form dy dx equals k times y, the solution will automatically be y equals d times e to the kx power. In this case, we see that the value of k is 2. So we have y equals d times e to the 2x power. We just need to find the value of d using the initial conditions. So substituting 0 for x and 1 for y, we have 1 is equal to d times e to the 2 times 0 power. E to the 0 power is 1, so this tells us that d is equal to 1. Substituting 1 back in for d, the equation becomes y equals e to the 2x power. We then could have used this to answer the question, what is the value of x when y is 3? So when y is 3, we have 3 equals e to the 2x, and now it's just a matter of solving this for x. We can solve this by taking the natural log of both sides of the equation. So we could do natural log 3 is equal to the natural log of e to the 2x. Natural log and base e are inverse functions which cancel each other out. So we end up then with natural log 3 is equal to 2x. Dividing both sides by 2, we get 1/2 times natural log of 3 is equal to x, which is exactly what we got the last time. Make sure you know this shortcut. If you have dy dx is equal to k times y, you can jump straight to here. Problem 2. Population y grows according to the equation dy dt equals k times y, where k is a constant and t is measured in years. If the population doubles every 10 years, then the value of k is which of these? Well, notice this is the shortcut that I was just mentioning. If dy dt is equal to k times y, that means we can skip straight to this solution. Y is equal to d times e to the kt. So anytime the rate of change of a quantity is proportional to itself, you can jump straight to this solution. We are told that the population doubles every 10 years. Let's pick some hypothetical values of population and time to help us solve for k. For example, let's say when time is equal to 0, the population is 1. I know that's a silly number, but I'd like to keep the numbers small. In that case, 10 years later, we're talking about time t equals 10, the population will have doubled, so the population will now be 2. So let's use these numbers to help us set up equations and solve for k. Using the first set of conditions that we just made up, we get the equation 1 is equal to d e to the k times 0. Then using the second set of made-up conditions, we get the equation 2 is equal to d times e to the k times 10. This is a system of equations. We have 2 equations and 2 unknowns. So let's start by solving the simple red equation. E to the 0 power is 1. So this gives us d is equal to 1. Now let's substitute this into the second equation and solve again. So we have 2 is equal to 1, which I won't write, times e to the, and I think I'll just put 10k power. So we need to solve this equation for k. Let's take the natural log of both sides of this equation. So that will give me the natural log of 2 is equal to the natural log of e to the 10k. Natural log and base e are inverse functions which cancel each other out. So we end up with the natural log of 2 is equal to 10k. Dividing both sides by 10, we get k is equal to the natural log of 2 over 10. Let's find the decimal value in the calculator. So it was the natural log of 2 divided by 10. 0.069. The correct answer is A. Problem 3. If dy dx equals 4y, and if y equals 4 when x equals 0, then y equals which of these? Well, this is that shortcut again. We have dy dx is equal to k times y. So we automatically know the solution will be y equals d times e to the kx power. And because of the 4 right there, we know that k is 4. So we have y is equal to d times e to the 4x power. So let's use the initial condition to solve for d. Y equals 4 when x is 0. So we have 4 is equal to d times e to the 4 times 0. E to the 0 power is 1, so that tells us that d is equal to 4. So the equation then becomes y is equal to 4 times e to the 4x. So that is option A. Kabam! Problem 4. During optimal conditions, the rate of change of the population of a certain organism is proportional to the population at time t in hours. At time t equals 0 hours, the population is 300. At time t equals 24 hours, the population is 1,000. At what time is the population 500? Once again, this is going to be the shortcut. The rate of change of the population is proportional to the population. When the rate of change of a quantity is proportional to itself, that's when we can jump straight to the solution. In this case, P equals D times E to the KT power. Let's use the initial conditions they gave us to set up equations that will help us find the value of D and K. So at t equals 0 hours, the population is 300. So plugging that in for t and p, we have d times e to the k times 0 is equal to 300. E to the 0 power is 1, so that tells us that d is equal to 300. So our population equation levels up and becomes P equals 300 times e to the kt. We still need to find k. So let's move on to the next set of initial conditions. At time t equals 24 hours, the population is 1,000. So substituting 24 in for t and 1,000 in for p, we have this equation. K is the only unknown, so we should be able to easily solve for it. Let's divide both sides by 300. 1,000 divided by 300 reduces to 10 over 3. I can get rid of the e by taking the natural log of both sides of the equation. Natural log and base e are inverse functions which cancel each other out. So that will leave me with 24k is equal to the natural log of 10 over 3. Dividing both sides by 24, we have k is equal to the natural log of 10 over 3 all over 24. Substituting this value of k back into the equation, we get this. Notice instead of putting natural log over 24, I went ahead and just wrote 1/24 in front, which is the same thing. The ultimate question is, at what time t is the population 500? To figure out when the population is equal to 500, let's take our population equation, set it equal to 500, and solve for t. Let's start by dividing both sides by 300. 500 divided by 300 reduces to 5 over 3. Let's get rid of this base e by taking the natural log of both sides of the equation. Natural log and base e are inverse functions which cancel each other out. So now we have this. Remember, we are trying to find t. Let's multiply both sides by 24 to move that over to the right-hand side. Now let's divide both sides by natural log 10 over 3 to get t by itself. Let's compare this ugly expression for t to the multiple choice options to see if we get a match. Dividing by 1 over 24 is the same as multiplying by 24, so the answer is D. Problem 5. The quantity R in grams of a certain radioactive substance decreases according to the exponential decay model dr dt equals negative 0.05 R, where t is measured in seconds. During an experiment, a scientist determines that the rate of decay of a second substance with the quantity S in grams can be represented by a linear model ds dt equals negative 4, where t is measured in seconds. If at time t equals 0, R at 0 equals 100, and S at 0 equals 125, at what time t in seconds will there be equal quantities of both substances? This is that special case where the rate of change of a quantity is proportional to itself. So we can go straight to the following solution. R is equal to D times E to the K T. However, in this case, we know what K is. This is K. So we have this, but we actually know what D is also. This D is always the initial amount of whatever it is. And they told us that R at 0 is 100. So D is 100. So we have this equation for the amount of substance R at time t. Let's see if we can come up with an equation for the amount of substance S at time t. We are given that ds dt is equal to negative 4. Let's multiply both sides of this equation by dt. So we get ds is equal to negative 4 dt. Integrating both sides of the equation. On the left side, we just have S. And on the right side, we have negative 4t plus c. We can use this initial condition to find the value of c. Let's plug in 125 for S and 0 for t. This tells us that c is equal to 125. Upgrading our equation for S, we now have S equals negative 4t plus 125. Notice that now we have an equation for the amount of both substances as a function of time. We are being asked what time t in seconds will there be equal quantities of both substances. But this is calculator active. So let's type both of these equations into our graphing calculator and see where they intersect. So hit the y equals button and type in both equations. You're going to have to use x instead of t. So normally I would hit zoom 6 right now. But if I do that, I'm not going to see anything. The reason why is because look at how big these numbers are. I got a 100 in the front here. I have a 125 at the end here. These numbers are very big. And my standard window is 10 by 10. So the graph is going on off camera. I'm going to have to adjust the window. So because of the 100s that I saw in the y values, I'm going to let my y max be like 200. I'm just picking a number that's well over 100. So let's call it 200. Now, how about the x max, right? This is the time. So I'm looking at my answer choices actually, and I see that the biggest answer choice is here at 30. So I don't need to go far past my biggest choice. So I think I'll let x max be, let's say, 50. All right, let's hit graph and see what we've got. Okay, this is pretty good. We just need to see what this intersection point is. So hit second trace, choose intersect, option 5, and move your pointer over close to the point of intersection, and hit enter. When it says second curve, just hit enter. When it says guess, just hit enter again. So this x is the time, this is really t, and it is 23.548. So the answer is C. Problem 6. A dose of 400 milligrams of a drug is administered to a patient. The amount of the drug in milligrams in the person's bloodstream at time t in hours is given by A of t. The rate at which the drug leaves the bloodstream can be modeled by the differential equation dA dt equals k times A, where k is a constant. Which of the following could be an expression for A of t? Once again, we have the special case where the rate of change of a quantity is proportional to itself. So we can use the shortcut and go directly to the answer. A is equal to d times e to the kt power. D is the initial amount of whatever it is. In this case, the milligrams of this drug. They told us that we are starting with 400 milligrams of the drug. So that's D. So the equation becomes A is equal to 400 e to the kt. So let's compare this to the options and see which one is a fit. The answer is option A, where k is negative 0.3. Problem 7. Extreme heat applied to a colony of microorganisms causes the size P of the colony, measured in grams, to decrease according to the exponential decay model dp dt equals negative 0.4 p, where time t is measured in hours. The size Q of a second colony of microorganisms, also measured in grams, decreases at the constant rate of 1 gram per hour, according to the linear model dq dt equals negative 1. If at time t equals 0, the first colony has size p at 0 equals 2, and the second colony has size q at 0 equals 3, at what time will both colonies have the same size? This sounds really familiar to problem number 5. This is practically the same problem. Here is the special case where we have the rate of change of a quantity proportional to itself. So we can skip straight to the solution. P is equal to D times E to the kt power. We know that k is negative 0.04. So that means P is equal to D times E to the negative 0.4 t. Because of this initial condition, we also know what D is. D is always going to be the initial amount of whatever it is. So D is 2. So far, so good. We have an equation for the size of colony P as a function of time. Now let's see if we can come up with an equation for the size of colony Q as a function of time. We are given that dq dt is equal to negative 1. Let's multiply both sides of the equation by dt. That gives us dq is equal to negative 1 dt. Now take the integral of both sides of the equation. The integral of 1 dq is just q. And the integral of negative 1 dt is negative t plus c. Can't forget the constant of integration. This initial condition allows us to find the value of c. When t is 0, q is 3. So that gives us 3 is equal to negative 0 plus C. So obviously C is equal to 3. Substituting 3 back in for C, and we have the equation Q is equal to negative T plus 3. So now we have an equation for the size of each colony as a function of time. To answer the question, at what time will both colonies have the same size, let's type both of these equations into the calculator and see where their graphs intersect. Hit your y equals button and type in both equations. You'll have to use an x instead of a t. Do we need to adjust the window like we did on the other problem? These numbers seem pretty small. I see a 2 and a 3, and looking at the answer choices, they're all less than 10. So I think a standard 10 by 10 window will be sufficient. So let's hit zoom 6. All right, let's see where they intersect. Hit second trace and choose option 5. Obviously, we're looking here in the first quadrant. All right, we don't have any negative quantities of these colonies. So move the pointer close to the point of intersection and hit enter. When it says second curve, just hit enter again. When it says guess, hit enter again. So the intersection is at x equals 2.156 if you round up. And this is really time. So the answer is C. Problem 8. During a chemical reaction, the rate of change of the amount of the chemical remaining is proportional to the amount remaining. At time t equals 0, the amount of the chemical is 12 moles. At time t equals 4, the amount of the chemical is 4 moles. At what time t is the amount of the chemical 3 moles? A mole is a unit of measure used in chemistry. The rate of change of the amount is proportional to the amount. When the rate of change of a quantity is proportional to itself, that's the special case when we can use the shortcut. Let's call the amount A. So the rate of change of the amount would be dA dt, and that is proportional to the amount, A. So, because this is that special case, the shortcut is we can go straight to A is equal to D times E to the KT power. At time t equals 0, the amount of the chemical is 12 moles. That gives us the value of D, which is always the initial amount of whatever it is. So now we have A is equal to 12 E to the KT. At time t equals 4, the amount of the chemical is 4 moles. So let's substitute 4 in for T and 4 in for A. So that gives us 4 is equal to 12 E to the K times 4. Let's divide both sides by 12. So 4 divided by 12, that's 1/3. So I have 1/3 is equal to E to the 4K. We can get rid of this E by taking the natural log of both sides of the equation. So I have the natural log of 1/3 is equal to the natural log of E to the 4K. Natural log and base E are inverse functions which cancel each other out. So I'm going to end up with natural log of 1/3 is equal to 4K. Dividing both sides by 4, I get K is equal to natural log 1/3 divided by 4. Substituting K back into the equation, we have A is equal to 12 times E to the 1/4 times natural log 1/3 times T. The ultimate question is, at what time T is the amount of the chemical 3 moles? So let's put in 3 for A and solve for t. Now let's divide both sides by 12. 3 divided by 12 simplifies to 1/4. So we have this. I can make the e go away by taking the natural log of both sides of the equation. Natural log and base e are inverse functions, so they cancel each other out. That's going to leave behind the 1/4 natural log 1/3 times t, which equals natural log 1/4. Let's multiply both sides by 4. We can get t by itself by dividing both sides by the natural log of 1/3. This is one form of the answer. Let's look back and see if it matches any of the answer choices. Well, I need to adjust this a little to make it match one of the options. So 1/4 is the same thing as 4 to the negative 1 power, and 1/3 is the same as 3 to the negative 1 power. We can simplify further using the following property of logarithms. The natural log of a to the c power is equal to c times the natural log of a. In other words, when you have the natural log of something with an exponent, you're allowed to put the exponent in the front without changing the value of the expression. In this case, I can take this -1 and put it out in the front. And I can also take this -1 and put it out in the front. I'm sure you see where this is headed. Now we have a negative divided by a negative, which is a positive. So the answer is D. Problem 9. A kitten weighs 85 grams at birth. During the first 4 weeks after the kitten's birth, its weight in grams is given by the function w that satisfies the differential equation dw dt equals k times w, where t is measured in days and k is some positive constant. Which of the following could be an expression for w of t? Well, this is, once again, that special case. We have the rate of change of a quantity proportional to that same quantity. We can solve an equation like this with a shortcut by saying w is equal to d times e to the kt power. Let's see, did they give us the initial amount d? A kitten weighs 85 grams at birth. That's the initial amount. D is always the initial amount of whatever it is. So the equation becomes W is equal to 85 times e to the k t. So I guess we can just take this and sort of compare it to the options and see which one fits. The answer is A, with a k value of 0.059.